Okay, hello everyone, and welcome to this first colloquium of the term and of the academic year. That's a great attendance. It's nice to see you all. And today we're especially delighted to welcome Professor Naoki Yoshida from Tokyo University. Naoki did his PhD actually in Germany, in Garching, so he speaks German. You can test him, or maybe not. And then continued to the CFA and then moved back to Japan, where he's now professor since 2012. Naoki has a very big group which does a variety of things, especially working on first stars and black holes, the growth of intermediate black holes, intensity mapping, also doing some participating in observations with ALMA and JWST. And without further ado, I'll pass the microphone to Naoki.
Thank you, Anastasia, and thank you everybody for hosting me this week. It's my real pleasure. I have been enjoying this week very much in many ways, and I also had experienced a real academic life in British Park, actually. So it's very enjoyable. Okay. Here's the contents of my talk today. In the beginning, I tell you a little bit history about this research. And then I move on to the standard part that I explain the physics of star formation and so on. And I add a few recent physics recently discovered or advocated. And then magnetic field as well. And then in the end, I talk about cosmology with the highest redshift galaxies. Okay, so yeah, although I look like very formal, like sorry, I know this is not a wedding party, but I just have a dinner afterwards, so I just decided not for this colloquium actually. Yeah, although I look very formal, I'm exotic in science and even extreme in computation. So don't worry. Please feel free to, if you like, the interrupt, and then I don't behave like a teacher. So don't worry. Okay. Okay, a bit of history. So this is development of astronomy, and in late 90s, I was a student at MPA, and actually back then I more frequently came to Cambridge to see George and other people. Okay, so when I was a student, this is the highest redshift. Then back then, people like my colleagues were really excited about redshift 4 galaxies, redshift 5-ish quasars, and say about redshift 1 supernovae for the detection of accelerating universe and so on. Okay, so even redshift 4 galaxies, they were calling them like primeval galaxies, which nowadays we call it like mature or evolved galaxies and so on. But as you know, the development afterwards is pretty impressive. Nowadays, it's our like daily routine to talk about redshift 10 galaxies beyond, redshift 9 gamma ray bursts, 7 quasars, even like redshift 4 supernovae, even like gravitational waves, which is reasonably away from us. So this is impressive. So I used to use this slide for like 10 years ago, but shamefully, my imagination was not big enough, so I stopped this by the 2020 or so. The horizontal axis was not enough. And now, you know, after JWST and so on, we see galaxies way beyond redshift 10 or so. Okay, so now I decided to, you know, even 10, 20, 40, 2070, or the next century or so. Okay, so young scientists, students, please take this over from me and please inherit this from me. 10 years later, so you start saying, okay, when I was a student, there was a guy came here talking about redshift 10 galaxy, very excited, and then you use this slide. So please do so. I'm happy to do that. But now, let's see. The question is, in the future, you might ask, you know, but it's okay, maybe we build a bigger telescope, but are there really like objects at redshift 50 or 100 or so? I promise I come back to this point at the end of my talk. But Anyway, this exploration continues, and then there are many exciting news on this high redshift frontier. Okay, so I talk about far stars. Interestingly, far stars are at the junction of many different topics like cosmology, dark matter, supermassive black holes, and black hole binaries, galactic archaeology, and so on. It's very interesting. It's really like the understanding the formation of far stars can really touch upon many different things. Okay? And especially I don't think I need to explain this recent excitement with James Webb, this superb capability of detecting a distant object. To me, the most surprising or good thing is everything is operating so fine. Like, there was a little bit problem with MIDI, but it's amazing this remote telescope is really operating very nice to discover many new things. So this is really, really nice. So one local contribution from your colleague, Professor Maiolino, he observed this particular galaxy GNZ11 like this. This is very luminous at redshift 11, so you notice already it is like galaxies beyond redshift 10 or so. Even more interesting is Professor Maiolino. He said he detects something very peculiar, possibly like line emission from helium-2 1640 angstrom that can be generated, likely from powered by hot stars or massive stars. AGN can do it, but according to their analysis, it's impossible to have this luminosity from AGN photoionization from the center of this main galaxy. So this can be very suggestive. Maybe the existence of hot massive stars away from this main galaxy, just right here. This is the helium-2 emission part. Okay? This is the distance frontier. Okay? The important information comes not only from the distant universe, but we can look at our backyard nearby. This is a particular star, Lamos J1010 also. It's a stellar relic in our Milky Way galaxy. It's a metal poor star. Its ion content is about 300ths of the sun or so. But it's not, this is like, we can find another star, for example, right? But if we take the high resolution spectrum of this star, it's very interesting. Like, very little signature of a sodium line. Magnesium too, it definitely has an ion feature with this amount. Even compared with the similar star with the similar ion abundance, this star has extremely small abundance of sodium and magnesium and barium and so on. Okay? So these alpha elements really, really like a small amount compared to other metal poor stars. Okay, this is like as a function of metallicity or ion abundance. This cobalt to ion ratio is also very peculiar, which is telling us something. So if we put these abundance patterns together, it's interesting. So these red points are observed abundances in the order of atomic number. Sodium, magnesium, all the way up to ion. So, okay. It turned out this peculiar abundance pattern, it is not really reproduced by the metal field of ordinary quark collapse supernovae. Okay. This low alpha ratio and a strong odd even pattern like we see here, it's not very easy to be reproduced by usual supernova, quark collapse supernovae. Okay. And its particular signature is this abundance of calcium over magnesium. So there are many other stars with this abundance plane. And the monstrous supernovae called Pair-instability supernova, it almost uniquely points to this place, a bit away from other stars. And then this Lamos star has the right abundance of this, meaning this is very likely the signature of Pair-instability supernova. What is that? This shows the evolution of very massive star. This is the core density and core temperature. A very massive star, it goes on high temperature, high entropy track in the core, okay, like this. And as the star evolves, there is an island called Pair-instability regime. That is that for high enough temperature, photons are energetic enough to produce electron-positron pairs. Okay? So effectively, by this pair creation, the photon gas pressure is lost as the electron mass, rest mass energy. Okay? So it's like, in the very hot core, if you push a little bit, it doesn't bounce back. It goes like runaway implosion. This happens during the oxygen burning phase. Okay, and in the end, this oxygen burning or explosive burning generates a huge energy of 10 to the 53 errors, causing complete disruption of a star. Okay. So because this explosion occurs at much lower density than the usual core collapse supernovae, the so-called neutronization do not occur. Okay. Neutronization is like making the abundance patterns like smoother. But because this process doesn't happen, we typically observe these strong odd-even patterns for the elements produced by pair-instability supernova. So that's why I say this is really the evidence that this kind of supernovae happened. Especially, we can also point to the mass, by fit of theoretical calculations. This points to the explosion of 260 solar mass star. Okay. This is very interesting. So if this is one example, and if I plot the mass distribution, still like one example, in this mass, like 10, 100, 1,000 solar mass, there's one case that suggests the existence of extremely massive star in the early universe. Very likely that progenitor star that exploded was the first generation star because of the low ion abundance we observe and that particular abundance pattern. Okay, so this is about the star formation in the early universe. And this is something I like with astronomy. Okay? I talked about the very distant galaxies and maybe monstrous black holes as we observe today in the very distant universe. On the other hand, we also hear a story about a small metal pulsar in our backyard. Okay? So these are seemingly very different, right? Very different in mass and very different in distance and so on. But they may have a common origin, okay? Like the first generation of stars, and which has element production that can be ultimately related to our own existence, like our body, the carbon, oxygen, and so on. They might be produced, at least partially, by these things. All right, so what was the origin? What was the beginning? In the beginning, it's very simple. This is like cosmology part. In the beginning, there's only a sea of light elements and dark matter and tiny ripples, density fluctuations, as we observe as CMB. This is the starting point. And thanks to the limited amount of element, in the early universe, there was only essentially two elements, like hydrogen and helium. So this is a simple picture of a primordial gas cloud back then, okay? So this is simple enough. I can even show this in kindergarten, not KICC. Okay. So the hydrogen helium gas, it's like self-gravitating until it forms a star. The gravity pushes, and the gas needs to radiate its thermal energy. This radiative cooling is operated by a trace amount of hydrogen molecules. That's how it goes from the cosmic diffuse gas to a star. Okay. In reality, it's not that simple. There are like many physical processes starting from the diffuse gas. This is the density and temperature plot for the evolution of a contracting gas, primordial gas. There are many things, chemical reactions, heating, cooling, and radiative transfer, and chemical reaction again, and so on, all the way from the diffuse gas to a protostar in this way. The density covers over 20 decks or so. But one can reasonably follow all of these processes in the early universe to say, to do calculations of star formation. Okay. I can only show the initial part, the structure formation part, but the detailed, further details can be seen from this YouTube video. This is a typical structure formation driven by dark matter and gravity, like this. And there is like some target object. Inside it, like, there's plenty of primordial gas of hydrogen, helium. Here I'm showing mostly like dark matter distribution, so that appears very clumpy. Now we can zoom into the particular star forming out of this box, hopefully. Yes. Okay, there's a small dark matter halo hosting the first star. It goes just a little bit beyond the real formation, showing this clumpy structure. Like this is the molecular gas cloud about the parsec scale. And it continues zooming in onto the star forming region. This is all from a single continuing simulation, not really the computer graphics or artist impression. The gas really contracts to the protostellar density. Okay. Because I show different kinds later, so I stop here and then move on to the main result. So by running this kind of simulations with all these important physics, we can really form on the computer these stars, especially massive stars. So this slide explains how the primordial stars are formed, like in one slide. The essence is the Jeans mass, the important mass scale, it's very high because of the high temperature of the gas compared to the contemporary star formation. Usually contemporary star formation nearby, it's like 10 Kelvin or below, but this case, the gas remains close to 100 or 1000 Kelvin. Okay? Similarly, because of the high gas temperature, the gas mass accretion, once a protostar is formed, the surrounding gas is accreted. Its accretion rate is very high, about 0.01 solar mass per year. This sounds small, but if you multiply this by 1,000 year, it easily gets to 10 solar mass or so. And in the early universe, by definition, there's no dust grains, no really radiative feedback by far UV, only ionizing radiation regulates the stellar growth or star formation like this. There's like a central star, and this is bipolar H2 regions. So all these environmental conditions are, in a sense, ideal conditions for massive star formation. There are, of course, environmental dependencies, cloud to cloud, star to star. They have different masses according to our calculation. The thermal evolution, they are slightly different depending on the degree of rotation of a molecular cloud. Typically, first rotation results in slow collapse and accretion. Okay? The gas mass accretion rate, they vary a lot depending on the object. And the final stellar mass is also very much different from, say, 10 solar mass to all the way to 1,000 solar mass or so. Nowadays, based on these simulations, one can come up with a very nice physical model, as your local colleague, Buyoran Lee, has been developing. Okay, so the main result, the resulting final stellar mass distribution from our simulation is like this, starting from 10 solar mass, all the way to 1,000 solar mass. This is not really IMF. This is like the mass distribution of the central object. Okay, so, I showed nice movie and I explained the physics of primordial star formation, but it's just nice, and then the simulation is simulation, and the result is like this. But funny enough. But then nice thing is we can now test against observations. I showed one example. right? This particular star suggests the progenitor stellar mass was 260 solar mass or so. Okay, there are some others. Another metal poor star by Keller et al., the abundance pattern, it suggests the progenitor mass was 60 solar mass, massive star. Okay. And there are another example like this. So the number of observations is still limited, so we can't really do the histogram thing. But interestingly, there are like, wherever we kind of predict peaks, we have like 2 samples here as well, and this wide distribution because of the variety of environmental conditions that can be reconciled, or what's say, in other words, observations, the variety is also explained by our models. Okay. One more important thing is progenitor mass beyond 300 solar mass, they are so massive that they collapse directly to leave remnant black holes. So that should be around until today in one way or another. Okay. So maybe this is just a speculation, but we know there are many gravitational wave sources locally, and then some of them, they have, typically before merging, they have very high mass, like even like 50, 60, or even 100 solar mass or so. Some of these might be remnant of first generation of stars. And indeed, my colleague Kazusugi Mura, he finds an interesting case where binary massive stars are formed in his simulation. So starting from similar gas cloud, the spiral arm instability produces these twins or binaries, and that they evolve sort of independently although with under mutual action. And then finally they produce like 60 solar mass, 70 solar mass binary population. These might be, it's still like wider separation, but this, maybe dynamically it might become a good gravitational wave sources. So here's another movie. It's similar, starting from a single molecular gas cloud, contracting. And now we zoom in onto that with this length scale. Contracting, it's an extreme resolution actually. And then the first one forms, and the spiral arm instability drives the formation of 1 or 2 of these protostars. Both are now accreting at a very high accretion rate, growing very rapidly. And eventually the stars begins shining and generating H2 regions. And from this, they are like, just looks like dancing together as a pair or so. And resulting like 60 solar mass, 70 solar mass or so. Well, hopefully, we can really observe this like in a direct manner, which is not just a dream. This is a proposed cosmic explorer experiments, the next generation gravitational wave detector. Spectacular thing is its horizon is even up to redshift 40 or so. If the merging of 30 solar mass, 30 solar mass black hole occurs at redshift 40, Cosmic Explorer can hear or can detect these merging signals. Currently, as you know, with LIGO and Virgo, the current limit is, say, way up to like redshift 1 or so. But with next generation, higher sensitivity and so on, this horizon really extends to essentially to the edge of the universe. So this is very promising, especially to find our first generation of massive stars. Okay, so far so good. I explained rather proudly and so on. But I still need to include a few more physics to make it really like realistic. Okay. Now, one thing is the cosmological part. Okay, of course, the formation of first stars that are affected by the early universe physics. What is that? In the early universe, there was a photon baryon fluid, and sound waves were propagating within gravitational potential of dark matter Okay, so this effectively like sound waves, like causing displacement of photon baryon fluid with respect to dark matter. Okay, that we really observe as Doppler peaks of cosmic microwave background. Okay, so the schematic picture is like this: the sound wave or compression and rarefaction happens continuously up to the epoch of cosmic recombination. Okay, this sound wave motions is imprinted as supersonic velocities in the early universe. So if we plot the density field in the early universe, like following a standard cosmology, just like this, just like CMB math at this scale, like 500 megapascal. So there should be also the coherent velocity motions at the supersonic velocities like this, the corresponding like a density field, velocity field. So the baryons do not really trace dark matter, but they are moving at supersonic velocities at high redshift. This is the effect explored partly by your local colleague Anastasia, making this kind of nice picture. Okay. This, of course, dramatically affects how the primordial gas clouds are formed and what's the mass of the final fast stars and so on. Today, I don't really go in detail, but the things that I explained so far is like this. When the wind was very weak, things are like that. There are cases or there are regions with strong wind, then a very massive object can form. There are regions with intermediate strength, then we tend to find like filamentary structure and star clusters and so on. Okay. So in terms of more like easier understanding, these streaming motions cause the offset of baryons with respect to dark matter. So you see this like horizontal, like sharp stream, literally stream feature. This is a simulation by Anna Shower. In one direction, the gas is displaced. And sometimes the gas cloud, they are also displaced. This is the displacement with respect to the virial radius of dark matter halos. Okay, so one can find this kind of offset. Gas clouds are not necessarily formed at the center of dark matter halos. More recently, I and my colleagues explored similar effect. There's a dark matter density field. There's a gas motion from left to right, and then this displacement causes the offset of the gas object with respect to the dark matter density field. So in the end, this gas object can collapse or gravitationally contract even without the help of dark matter halo gravitational potential. Okay. So in one case with our UCLA colleagues, we explored a little bit. Essentially, we look for many interesting objects in simulation volume. And then we find, again, the same thing meaning outside of the virial radius of a galaxy, there is a small gas clump, not hosted by dark matter halo, but it's contracting by its own self-gravity. In the end, it's like this star cluster. This star cluster is orbiting around the main galaxy in this way. So this is a bit similar to the configuration that Professor Maiorino found in the observation of G and Z11. So the star cluster possibly displaced from the main galaxy and so on. More interestingly, because without the help of dark matter gravity, the contraction is small, so the corresponding G's mass is actually large, okay? Compared to the ordinary case of 500 solar mass, this is like even 100 times larger. So this would be a good site for formation of a star cluster in mass. And I found, interestingly, many years ago, Jim Peebles kind of predicted or like advocated maybe the globular clusters and other star clusters are formed in similar way out of a primordial gas and contracting with dark matter and so on. Okay, star cluster evolution, perhaps I should skip this time. I'm happy to talk and then evolution of black hole, but let me skip for now. Okay, so that one kind of new effect I explained, this purely cosmological origin. And the other effect that I have been just overlooking is a magnetic field. Okay, so in reality, in this simple picture, we should add the some small amount of magnetic field. Conventional wisdom is, the primordial gas is largely neutral. The ionization degree is less than 10 to the minus 4. So it's even if magnetic field exists, it doesn't really react, or there's no obvious generation mechanism and so on. It's not a plasma. But I started thinking more seriously after I thought about these streaming motions and the offset with baryons and dark matter. Here it is. Okay. So this is the mechanism of process proposed by Smadal and Ramesh Narayan 10 years ago. So this is the typical induction equation of magnetic field. And there is a battery term here. So this says if the fluctuation of ionization degree and the fluctuation of temperature, if they do not trace each other, if they have cross term, this can serve as a battery term to generate a net magnetic field. Okay. So these people, they did a fine calculation using linear theory, calculating temperature fluctuation, density fluctuation, temperature fluctuation, electron ionization degree fluctuation, and so on. And they found, because of the streaming motions, the density is suppressed, and so on. They can really generate the sizable effect of this battery term. The resulting strength is tiny, 10 to the minus 25 or 10 to the minus 24, but it's good enough as a seed, as a cosmic or a primordial magnetic field seed with this amount. And also it's linearly growing because of it's basically linear scale effect. So I was fascinated with this idea. At least, we want to include this effect and to see what happens. Okay? So to this end, I used the sort of one of the most accurate initial conditions, incorporating the velocity effect, this coherent streaming motion, and the resulting density suppression and the magnetic field generation as well, okay, following the prescription of Naos and Narayan. Okay. The result is like this. The gas density at redshift 17, there are many star-forming regions like this. This is usual, as I showed in my previous slides. Okay. The corresponding B field amplitude, for this I run MHD simulation to see just the growth of these seed magnetic field. So in the collapsed regions, the amplitude goes up to 10 to the minus 18. So certainly this is unimportant dynamically, but it again can serve as a seed to further amplification also. I also find very amusing, it's in this region, the large scale filamentary magnetic field is generated, just tracing the underlying density field also. Well, unfortunately, we usually use best simulation, best hydro simulation, and free resolving, adaptive, refinement, moving mesh, and so on. But unfortunately, we never really resolve the internal turbulence, subgrid turbulence, scale turbulence within one cell. So beyond this point, we need to rely on some modeling of the turbulence and the turbulence-driven magnetic field amplification. So here I just follow the say classic theory of Kazantsev and the modern version by Karlsruhe, Lazarian, and so on. So effectively, we need to really assume that each cell contains a spectrum of turbulence, okay, with this familiar power law. And then there's a theory that predicts the field amplification. This is magnetic energy amplification. At some point in the phase called the kinematic phase, it grows exponentially with this factor. So in this kinematic phase, the smallest areas of the turbulence, they are driving the turbulent dynamo. Okay, so this is the growth rate or turnover rate is given by this viscous scale. So essentially, it's impossible, but we need to really resolve down to Kolmogorov scale if we really want to do this in the numerical simulation. But it's certainly miserable. So we need to do like subgrid modeling like this. So the results are still uncertain. This is one example by Chris McKee. So as you see here, starting from the seed magnetic field, this kinematic phase really amplifies by this small-scale turbulent dynamo by many orders of magnitude until it goes to the nonlinear regime where the back reaction of magnetic field becomes important, and eventually like a saturation period or so. So this paper by Chris McKee, it does really reasonable approximation assumptions, but it seems to me taking a little bit extreme case of really amplified magnetic field. But the important point is, once this amount is really generated in the pre-collapse phase, then the effect becomes dynamically important in the post-collapse protostellar evolution stage like this. So this is the same object with and without magnetic field. In this case, we see like multiple clumps and multiple protostars forming. But in this case, since the magnetic pressure kind of suppresses the fragmentation, it remains as being a single object or so, at least in the first 1,000 years or so. So unfortunately, today I can't really give you very accurate definite answer, but there have been some other studies exploring how the initial magnetic field affects the evolution of primordial protostellar disks or protostars. So this is one example by Charlotte et al. This is a parametric study starting from 28 microgauss or 1 femtogauss and so on. The conclusion is the same. Eventually it becomes dynamically important to support the protostellar disk, and they tend to, with magnetic field effect, they tend to produce more massive stars with less fragments and so on. Right. Okay, that's with this uncertainty, with many things to explore, I can stop this first star formation part, and the remaining thing. I want to go a little bit extreme, as I said in the beginning. Let me use the next 10 minutes or so by talking about a bit of cosmology. Okay. So as you know, many of you know, and many of you appreciate the success of the standard lambda CDM. This picture depicts the abundance of objects with a variety of mass from galaxy clusters to galaxies or even like small galaxies and so on. This is a mass spectrum, but essentially it's like reflects density fluctuations, primordial density fluctuations. So it also compares with the observations of CMB, galaxy survey, clusters, and Lyme alpha forest and so on. And this beautiful agreement, this line is like a 6-parameter lambda CDM model that we enjoy. This is really the success of our standard model. Okay. But at least the success is limited to large scales. Okay. Sorry, this case, the horizontal axis is swap. Right? This is now the density fluctuation power spectrum. So this is large scales, small scales. Okay, and this is fluctuation amplitude. Essentially showing the same thing. This is CMB observation, galaxy clustering, and Lyme alpha forest gas clumping, and so on. And again, this success of the standard model continues. But interestingly, if we look at many smaller scale structure, galactic structure, say by strong lensing, or even if we look at the structure of our Milky Way dwarf galaxies by sophisticated analysis, there is an interesting indication or hint. Maybe this power spectrum at the small length scale is showing some turn up. This is very like just a hint. And of course, with a lot of uncertainty here like this. But this is amusing. It's way more complicated to infer the fluctuation amplitude at galactic scales. Like we need to look at closely the fine image of lensing structure, whether or not the underlying density field is clumpy or smooth. We also do substructure lensing using armor if this flux anomaly is consistent. we look at the velocity dispersion, stellar velocity dispersion of local dwarf galaxies. If this is sort of consistent with CDM, we need excess power and so on. Okay. The reason I bring up here is this. Recently, we also hear from JWST that maybe there are more early galaxies than expected, than even extrapolated from Hubble observations and so on. This is a particular example showing the stellar mass density in a unit volume as reported by Ivo Rabe et al. For Redshift 9 and Redshift 7.5. So I know there are many follow-up observations and there are like many interpretations and so on. But here, the next 10 minutes, let me be a naive boy who believes in whatever JWST discovers, okay? I'm just continue being a naive boy. So this is, obviously this stellar mass density is very large compared to our expectation. The one nice example is this by a plot by Michael Boylan-Kolchin showing unless we really invoke efficient galaxy formation, efficient means all the available baryons are converted into stars. It can't really explain this abundance of stellar mass or stellar mass density. Similarly, for UV luminosity function, there are many, many papers touching upon this topic. But it seems to me, even without being a naive boy, it seems to me there are really like many more galaxies than we expected. Okay, if you disagree, please disagree at the end of my talk, okay? Now, here comes my sort of serious idea. So what if, of course, we have a handful of observational limits at small length scales, Lime alpha and so on, but there's also like observational hints like this. So what if we think about a cosmological model with enhanced small scale power? That's a pure question, but it's interesting enough in the context of recent JWST and other observations. And interesting enough, as usual, my particle physics colleagues, they always say, well, sure, there are many early universe physics that can realize this kind of small-scale power enhancement, okay? Like singularities, like adding Carbaton, running mass, action-like models, even prime model black holes, and so on and so on. Even Alex Stravinsky, he himself considered this kind of enhancement. Anyway, so there are like plenty of possibilities to explore, or maybe observationally to constrain. So what happens if we add small-scale power here? It's very dramatic. If we look at the Redshift 9 structure, just like we observed by JWST, this is a prediction, a calculation by the standard CDM model without any enhancement. It's really like flat. The number of galaxies is very small. Only a slight enhancement, we suddenly see this clumpy structure at the same epoch. There are more galaxies like this. I found interesting side effect, a byproduct at Redshift 9. If we add more power, then we typically see these clumpy galaxies, maybe just like we recently observed with JWST result. Nice thing is, I know this is not a lecture, but nice thing is the adding a small scale power does not ruin the success of lambda CDM at large length scales, because this is virtually the same. Now this is like a 50 megaparsec volume, large scale structure. It's essentially the same. It doesn't do anything at the present day epoch. Only at high redshift and at small mass scales, like galaxy scales 10 to the 8 to 10 to the 11, the abundance is very much different by this enhancement of small scale power. Now again, galaxy clusters and so on at present day epoch, it doesn't change very much. So this is one way. Or in other words, we really need to look at high redshift universe to prove this small scale prime model power spectrum. Okay? The conclusion is simple, as one can naively expect. The observed stellar mass density with this enhancement, this is particularly this red curve, we can easily reconcile even without invoking the very high star formation efficiency. We don't need to do anything for the galaxy formation part. It's just a halo abundance driven by the enhanced small scale power. we can also do a little bit of exercise for the UV luminosity function so that we can also get reasonable fit to the Hubble UV luminosity function by going through this simple exercise. So this may be one way to use JWST observations to do cosmology or to prove early universe physics or to prove density perturbations at early epochs. Okay. One thing I want to say is, I didn't do this work. I did this work not because of the JWST result. I actually did many years ago. So I explored already with David Sparger already 8 years ago. We explored this possibility. So that's why I'm happily talking today about this power spectrum enhancement. Finally, what happens to the fast stars? It's very interesting. So if we allow, or if we really go into this enhanced small-scale power, the epoch of fast star formation goes, say, beyond redshift 50 or so, even like redshift 200. So there should be like these star-forming regions and so on at redshift of 200. I wouldn't say this is a prediction, but this is a nice direction to go. And then, in the end, we really want to observe or test observationally by a variety of methods. Okay, so I came back to this topic. Initially, you might have wondered, well, are there really like objects at redshift 100 or so? But maybe, I don't know, if we believe these recent discoveries and some observational indication, there might be some objects, and this red arrow touches really like redshift 100 when I celebrate my 100th-year birthday. So I'm really looking forward to it. So please inherit this plot. All right, to summarize, I told you about a lot of physics of primordial formation, but that's about it. It's like doable. It can be understood within 1 hour or so. So that's simple enough. And I showed a fascinating possibility of detecting the relic of the early universe. And I talked about a little bit of new physics coming into this star formation. And finally, I talked more, maybe to some of you, more interesting, doing cosmology with high redshift observations. Okay, I said what I wanted to say. Thank you very much. Thank you.